Hello, I'm Koichi Sanaka. Today, I will present our work at Asset Portfolio Optimization via Policy Learning. In online advertising industry, advertisers submit a set of ad assets to the platforms, and then a selection algorithms display optimal ads for users. However, even with sophisticated selection algorithms, the ad selection can fail depending on the given set of ad assets. For example, few ad assets limit optimization, while too many ad assets increase exploration cost. This leads to our main question: which ad assets should advertisers submit to the platform? We call this problem ad asset portfolio optimization, AdPOP. Conventional ad selection consider which ad asset to display from a fixed portfolio. In contrast, we consider which ad asset should be included in that portfolio. This problem is becoming increasingly important because large language models can generate so many ad candidates at low cost. Our goal is to identify the portfolios that maximize the final downstreaming reward. We formulate AdPop as a contextual combinatorial bandit. First, we observe the context X, such as a platform or a campaign. A policy then select a portfolio A represented by a binary vector. After that, we observe a reward R, such as a click or a conversion. Our goal is to optimize our portfolio selection policy using log data. Next, I explain the limitation of existing approaches. We categorize existing approaches into exact and independent approaches. First, the exact approach treats an entire portfolio as one action. Because the number of portfolios grows exponentially, regression-based methods suffer from estimation error, and the policy-based methods suffer from high variance due to importance weight. Second, independent approaches run the value of each others independently. These approaches can avoid combinatorial explosion, but cannot deal with interaction effect among ad assets. To address these problems, we propose ad asset portfolio optimization via meta-information, AdPOM. The key idea is to decompose a policy into two policies using meta-information. The first stage policy selects meta-information such as portfolio size and the degree of diversity. The second stage policy then selects the portfolio based on this meta-information. Based on this decomposition, we optimize the overall policy by two-step procedure. When we optimize the first stage policy, we use the AdPOM gradient estimator. The AdPOM gradient estimator applies importance weighting only to the meta-information rather than to the ad asset portfolio. This greatly reduces variance compared to the exact policy-based approaches because the meta-information space is much smaller than portfolio space. When we optimize the second stage policy, we first estimate the structure of expected reward function based on the meta-information. If meta-information include the portfolio size and diversity strengths, we can estimate the expected reward like this. Then we add asset one by one according to the estimated expected reward. This allows the second stage policy to consider interaction effect among ad assets without estimating the reward of every possible portfolio. Finally, we conduct synthetic experiment. This figure varies the strength of interaction effect in the true level function. The exact approaches always perform poorly because of the large portfolio action space. In terms of independent approaches, their performance gradually decreases as interaction becomes stronger. This is because they ignore interaction among others. In contrast, AdPom consistently learns high-performance policies across every interaction strength. Next, we value the number of candidate ad assets. As the number of candidates increases, the number of possible portfolios grows exponentially. The exact approaches continue to suffer from the large action spaces. The independent approaches avoid this combinatorial problem, but their performance remains low because they ignore interaction effects. In contrast, AdPalm performs best across all settings. This result shows that the AdPalm algorithms have advantage in the challenging situation. This is conclusion. We study asset portfolio optimization AdPop for the first time. We propose AdPalm algorithms. The key idea is to decompose the policy into first and second policies. The experiment shows that AdPalm can learn effective policies with challenging situations. Thank you for attention.